Owen. I'm here with my lab mates Cody, Mike, and Sung Kim, and we're representing UPenn. Our proposal is called PR2 Grasp, from perception and reasoning to grasping. The proposal was led by my advisor Max Likachev, and it also includes these 7 other professors here. So there is a lot of work that we're planning on doing from all different labs, and I will be presenting the work from the other professors that aren't here, and they'll just be high-level presentations because I don't have many details from their slides. Something that is cool about Penn is that we've been using ROS since the beginning, since 0.4, about a year ago. Here are 5 major platforms that we use that run ROS, and we also have a ROS lab for master students, mechanical engineers who are afraid to install Linux on their laptops but want to become friends with ROS. So they really appreciate the fact that they can do it, become friendly with Linux and ROS before they install it on their laptops. These are the 8 major research goals that we have for the PR2. The first project here is planning for autonomous opening of spring-loaded doors. Last summer I was here at Willow and I worked on with Sachin Chita planning for opening of regular doors. That was great and all, but there are a lot of doors that are spring-loaded. Spring-loaded doors are all around us, fire exits, bathroom doors, and we want to be able to open those as well. We want to extend the search-based planner that we wrote last summer to be able to open spring-loaded doors, and it adds challenges. These challenges are that you can't just swing the door open, leave it there, and then have the PR2 go through it. So now we're looking to create a principled approach, pretty much extend our previous planner so that it could complete full motion to open the spring-loaded door either with 1 arm in the base or 2 arms. And the cool thing about the planner is that it's able to plan a collision-free trajectory for the complete robot. We want it to also be able to handle right-handed doors, left-handed doors, or cabinet doors, or any form of door, so that it's not hard-coded, and we don't need any more hard-coded algorithms out there. It's just going to be a generic door planner. So this is the PR2 pushing open a door from last summer. This is PRF, I believe. This planner is also capable of pulling open doors, but for the sake of time, we're not going to show that here. So this is some haptics research that we're planning on doing, transferring natural handheld objects between PR2 and human and the PR2 and other robots. So I find this pretty cool because I research manipulation, and I just think about getting the gripper to the goal pose, but I have no clue what happens after that. So we're looking to make interactions between the PR2 and humans more natural, such that there isn't an awkward pause once you get the PR2's gripper to the goal. And the human has to try to figure out, hey, when should I try pulling this object out of the gripper, or how to have this social interaction that's normal between humans, how to make it normal between the human and the PR2. This project is a project by CJ Taylor, who's here. It's the Pinocchio project. The goal is to create a form of teleoperation for the PR2, such that using a motion capture system, you could have a human being do some action, and it will be mimicked accurately by the PR2. At Penn, we have 2 pretty nice Vicon systems, so I think the goal is to use the Vicons in the beginning and then move over to a more realistic form of mocap so that it could be used in a home or whatnot. Last summer, Mark Yim was here, and he made a changeable end effector for the PR2. And his goal for these coming years is to continue that and make some standard interface for building a PR2 gripper and then having a good robust way to change the gripper on the fly depending on the task. So there are many challenges with doing that, and you can see them here.
All right, there's 2 basic parts to changing the end effector. One is putting the current gripper away, leaving the forearm open to attach another end effector. And then the second part is to attach that second end effector. The tricky part about attaching the second end effector is inserting that stub into the gripper. And the way we did it was by actually just pre-recording the motions of the arms.
To present our goals for planning in dynamic environments, I'm going to give you Mike Phillips.
Hi, my research with my advisor Max Likachev is on planning in dynamic environments. Motivation for this problem is that household tasks, any household tasks, you're going to have to deal with traveling from one place to another around humans and pets, and dynamic obstacles are just a huge part of our world. So this is a really important problem to make sure the PR2 can get from one place to another without inconveniencing or injuring people or pets. The problem is basically given a map, the pose and the goal, and some predicted trajectories of dynamic obstacles. We'd like to generate a time parameterized path that gets us from the start to the goal safely. The most common approach for this kind of problem is to treat the dynamic obstacles as static. This is currently what's done with MoveBase and things, and it's done in most applications. The problem with this kind of approach is that you're not necessarily guaranteed to find a path to the goal. If your dynamic obstacle is in a tight hallway or blocking the front of a hallway, there may not be a solution from the robot to where it wants to go. But if you add a time dimension to this problem, you realize that the obstacle is moving and there actually is a path that gets you from the start to the goal shown on the right. But adding this extra dimension makes the search space very large and makes it difficult to compute this path. What we'd like to do is take advantage of the fact that dynamic obstacles generally take up a small amount of the space in the environment and come up with algorithms that can get fast planning times while still getting optimal paths. This is some previous work with Alex Kushliev and my advisor Max, and this is a approach. He uses a time-bounded lattice, which just puts a finite horizon on the search space, so you plan in time for up until a certain point, and then after that, you plan without time in order to get fast, quick, generate paths quickly, basically. And you can see the robot is trying to get to the other side, and is eventually allowed to get through. This video is a planner that I'm working on right now. Here, the robot is trying to get to the right-hand side. All the planning times in the examples that you'll see in this video are under 1 second. The video is actually sped up 2 times, but that's purely because we only have 15 minutes to present right now. Here, the robot wants to get to a goal on the left. My goal is to implement this planner on the PR2 now that I have it working in stage in the Rust simulator. And here, this robot wants to get to a goal on the right, and it figures out that it has to go into this notch at the bottom in order to let the obstacle go past. Another project that I'm going to be talking about that's happening at Penn is with John Boshi and Max Likachev. This is about tracking people. Essentially, the idea behind this project is that there's a lot of people. The robots need to be able to detect people in order to see where they are and what they're doing. And one of the approach that they're taking is that by using planning, we can predict where people are likely going to be in the future. And therefore, even if there are occlusions, we're able to robustly continue to track those people when they become visible again. And I'll mostly just show the video. I think it does a better job than my explanation. So, here in this video, you can see there's these boxes drawn around people. The one box shows the people we're trying to track, and you'll see that even with occlusions, the tracker still manages to work because certain goals are predicted for where the person may be going in the future, and then a planner is run in order to generate possible paths that the human might take, which makes it more robust to occlusion. So I guess I'll pass it off now to Cody.
Thank you.